Morning everybody, this one's a different type of video. As you know, this one you're scrolling through just to find the things that you're having trouble with after you did your worksheet. So I'm just gonna jump right to it, and I know that you might be popping in at different points when you see it, so I'll always start with showing the blank slide and then going right to the next one to explain why the answers are the way they are. Okay, so in this one, when you're trying to figure out decay or growth, remember, you look at the number that's raised to a power to decide if it's decay or growth. And if it's a number bigger than 1, it's a growth. And if it's a number smaller than 1, it's a decay. Now, as far as the y-intercept goes, if there was only a number to a power, it would be 1. So you find the y-intercept by the number that's multiplied out in front here. So each one of these are y-intercepts. Remember, y-intercepts is what you get when you plug in a 0 for x. So anything to the 0 power is 1. And so that's why this number turns into its y-intercept. Now in the graphing, remember you're looking for making sure that you have a very nice curve on that. I'm looking for at least 2 plotted points, one of them having to be the y-intercept, okay, and one of them being another point, but be careful also how low the graph goes. Okay, now as far as your bottom, where that goes, that would be if there's any other number out here that shows how low it would go. Okay, if there's no number here, then the lowest it would go would be x-axis. In order to find the y-intercept, just plug a 0 in here. So 3 to the 0 is 1, 1 minus 1 is 0, so there's that point. 2 to the 0 is 1, 1 plus 1 is 2. And then to find your next point, just go 1 over from that and plug in the number. So when we plug in a 1 here, 2 to the first power is 2, 2 plus 1 is 3, you've got that. I've got some other points in there too, but I've explained to you how you would make sure that you've got them, but I want to see at least 2 clearly graphed points, and I want it to not go down too low. Okay, and I am figuring out how I'm going to test you on that, whether it'll be like a multiple choice type of a thing, but these are what I'm looking for here. Once again, 3 to the 0 power, we already figured out the y-intercept. When you plug in a 1, 3 to the first power is 3, minus 1 is 2, and there would be your 2 points, and a very nice curve on that one. All right, logarithmic form. Remember, logarithms deal in bases and exponents, so this one will be log base 5 of 25 equals 2. Okay, so all of these, the base is your base of your logarithm. Here it is, even if it's on the other side. The number that it equals is the number you're taking the logarithm of. Okay, and then the final exponent is actually the answer. So this is saying 5 to the second power equals 25. Okay, all right. Evaluating the logarithm, you're asking yourself the base to what power gives you this number. Okay, so 2 to the 4th power, 3 to the 4th power, 5 to the 2nd power, and 4 to the 3rd power, all will give you the right answer. So when it's saying evaluate the logarithm, you're just looking for a single answer. Again, 2 to the 4th power is 16, 3 to the 4th power is 81, 5 to the 2nd power is 25, and 4 to the 3rd power is 64. Okay, now these are your interest formulas. You have 2 different things happening. This one is asking for if you're just getting the annual interest. This one is saying if it's compounded continuously. This one is compounded annually. All right, so our formulas look a little different. You get different numbers. Okay, on this one, you take the amount that's invested, and it equals 1 plus the interest rate to the power of the number of years. Okay, so when you put that in, you'll get a number like this. All right, to remind you how that looks. Okay, 8,000 times 1.05. My 1 didn't come out. 1.05 to the 9th power. Okay, like that. So be careful that you're doing your powers correctly. This one is PE to the RT power principle, that natural base 2.718. But what you're going to do on your calculator, 8,000 times, and where's your E? Your E is the second of the natural log, and 0.45, which you got by multiplying your interest rate times your number of years. And then you end up with this. You're rounding to the pennies place, so please be careful that you do that correctly. This rounded up ended up making it a whole 50 cents, and since it's money, make it look like 50 cents, not just 0.5. All right, so you've got that. All right, then we had the Richter scale problems. There were a few of you that asked about this, so here we have it so that you can do it correctly. Our basic formula looks like this. The ratio that compares the intensities equals when you take the larger one minus the smaller one, and then you get a number. And then because of log without a base means log base 10, this is really saying that the ratio of the intensities equals 10 to the 2.4 power. And when you've done 10 to the 2.4 power, remember the caret means that, 2.4, you get about 251 times stronger, that this earthquake was that much stronger than this earthquake. Okay, so you set it up, the calculations go straight into your calculator with that. Okay, and if you, let's just move on. Then if you have a specific parent function, you can talk about the shifts. Now, one problem that I was seeing that some people were doing when they were trying to make the graphs, they were trying to do them directly using the shift method, but not taking into account what the original graph would have looked like. So you've got to be very careful with that. If you know what the parent function looks like, then definitely you apply the shifts, and that's what we're doing here. But if you don't have a clear picture of what the parent function looks like, you can't actually draw the graph directly from it unless you draw the parent function first. So be careful on that. Now remember, the number that goes with the x's is the one that tells you left or right. This one tells you up or down, and this one tells you compression or stretch. So compression of 1/5, right 2, this one's the one that seems backwards, and up 5, this is the one that seems natural to you. Stretch because it's a number bigger than 1, left 1, down 7. Stretch because this number is bigger than 1. Doesn't matter what this number is, it's the extra number out here. Stretch of 7, left 8, down 2. And compression because this number is smaller than 1. Compression of 2/3, right 5, up 1. I'm not going to have you actually graphing those with all that happening, but it's for you to know what's happening with this. Okay, next type was, okay, well, what is the transformation with a logarithm? And it follows the same rules. Sorry about that. So, for example, this one would be right 3, up 5, and left 8, down 3, simply because of what happens with the h and the k, like it does with all of the functions. Okay, then we have the whole thing with applying the properties of logarithms. And so what we have here is you need to apply them so this 4 can get dragged up top here. And then the plus makes it into a multiplication problem like this. Okay, the 4 got dragged up top. You can evaluate 5 to the 4th power. And then this plus turns it into a times to get your final answer. The 3 that's out front gets dragged up as an exponent, and then the minus turns it into a division problem. This 2 gets dragged up here to the top, and then the minus turns it into a division problem. So you're practicing those rules of logarithms because the logarithms do deal in exponents. The rules are more similar to exponents than for anything else. Expanding the logarithm going in the other direction. So this would be where the exponent gets dragged around to the front, and then it goes the other way. So here we have this exponent coming around to the front, and then your division turns into a minus, and finally you can distribute to get it simplified. This one, exponent dragged around to the front. This one, exponent dragged around to the front. First step. Second step, expanding. If it's a multiplication problem, you expand it to being an addition of logarithms. And then finally, if there's another one here, this one's hiding because 4 can actually be written as 2 squared. So you have another one coming around and you can bring this 2 to the front then. So always check after you've gone in a little while to see if there's any hidden powers. Like here, this 9 is a hidden power. So to make it completely expanded, you have to bring that other 2 to the front. So be careful with that. Okay. Then evaluating the logarithm. So in the easier ones, we would say 2 to what power gives you 15. But we have a problem here because there isn't an obvious number for that one. So you have to use a change of base formula. Remember what you can do is you can take the logarithm of this one over the logarithm of this one, and it becomes a calculator problem. The log of this one over the log of this one. We've changed them both to base 10s, and in that way you can let the calculator do the work for you. So we can hit log of 15 divided by the log of 2 and that giving you the 3.907. Go ahead and round it to 3 decimal points just in a standard way so you're used to what you're going to be typing in. We want to make it as standard as possible just for the ease of you entering it and knowing what to expect. So here once again, log of 7 divided by the log of 8. And giving you about 0.936 for that. Okay, so we've got that. Then moving right along. Once again, properties of logarithms. So if you're going to use the properties of logarithms, it means you have to put it into its own single logarithm. As long as you have the same bases, then you can do that. I'm not trying to trick anybody on this problem. So that means you can make it into a division problem. Okay. And you're really taking the log base 3 of 81, and that's something you can do in your head. 3 to the 4th power is 81, so your answer is 4. This one with the minus turns into its division problem. Simplify 75 divided by 3. 5 to the 2nd power is 25, so your answer is 2, giving you a nice answer. So our purpose for our simplifying the logarithms. Okay, and then another one that you can solve, you can do either where you notice that you've got a common base and avoid having to use logarithms at all, because this one will be 2 to a power, this is 2 to a power, this one's 3 to a power. These don't have anything in common, So you would have to take a log of both sides possibly to do that, and there's not even anything that approximates a common base, so you would end up having to do just a log base 10 of that one, or a natural, or oops, I skipped one. There we go. Here it is. A log base 10 for that one. So over here, because this one is 2 to the third power, these are they have to be to the same power to get the same number. So you can solve it then with your algebra. 3 to the fourth power, so very nicely these two equal each other, and then you solve. This one, like I said, there's nothing that even approximates a common base, so you can take the logarithm of both sides. Then use your rules of logarithms by pulling this down around the front. Dividing. Be careful you're not taking the logarithm of 12/7 here. It's the log of 12 divided by the log of 7, and giving you your answer like that. Same here, the logarithm of both sides, because it does work, and then bringing it down like that. Okay, and then we've got our nice natural logs with our base of e here. So if you want to get rid of the base of e, you have to use natural logs. So the natural log base e of 12 equals x. Log base e of 12 equals x. This is natural log, so directly in your calculator you just use your natural log button. Natural log of 12. So 2.485 if you were doing that. Natural log of 5. For this one, same reason, because it's log base e of 5 equals x. This one, you have to bring this over by dividing both sides, so that you can then use your definition of logarithms, 10 to the third power, or 10 to the 3/4 power, and then put that directly in your calculator, 10 to the 3/4 power. Don't forget, you do have on your phone or whatever, you've got calculators. Most of these things are in here. 10 to the x power is even there, and you can put that number in. For whatever reason, this is being weird today. That's okay. I can go back. I'll see if I can get that to work in a second. Let's try one more time. Here it comes. Oh, but it's not working again. That's very odd. Anyway, hopefully your calculator is going to work well for you on your phone. But I had showed you how to do that in another lesson. So 10 to the 0.75 power, and I've shown you on the other calculator. All right, so again, solving. When you're solving them, you have to use the properties sometimes. So for example, right here, you're thinking we have no powers, but we do have this, so you're thinking multiplication. So log of 6x equals 2. 10, because it's a base 10, 10 to the second power equals 6x, and pretty easily solved there. Okay. If you're having natural logs, you can use e to the second power equals this number, e to the fourth power equals this. Okay, e to the second, e to the fourth, and then you can use your e to a power button on here. So here, here's e to a power. E is also hiding over here, so we've got it in a couple different places. But we can do e to the second power if we need to start, and whatever power you need to on that. And then you can just add 5 and divide by 3. Okay, that one's nice. And then here, once again, you're trying to isolate your e so that you can use natural logs. So think of it as one whole big giant variable to start with. So adding 1, dividing by 3, and then you're just doing the natural log base e. So what natural log of 4 equals the exponent 5x. And then plug it in and get your answer. So there, we've gone back over them. I hope you're doing well, and I'm praying for you guys to do great on your test coming up on Monday. All right, God bless.